Okay, part two. The theorem we want to prove here is if n is a positive integer and a is real, a being greater than or equal to -1, then 1 plus a, that quantity to the nth power, is greater than or equal to 1 plus na. By induction, step 1, show p of 1 is true. So plug 1 in for n in that expression. So we get 1 plus a to the first power. Will that be greater than or equal to 1 plus 1 times a? Well, the left side is 1 plus a, the right side is 1 plus a. And 1 plus a is indeed greater than or equal to 1 plus a. So we got p of 1. Second step, assume p of n. Or in other words, we're going to assume that 1 plus a to the nth power is indeed greater than or equal to 1 plus na. And think about what we want to show. We want to show p of n plus 1, which is 1 plus a to the n plus 1 power. We want to show that that is greater than or equal to 1 plus the quantity of n plus 1 times a. So let's start with what we just assumed to be true. Start here. That 1 plus a to the nth power is greater than or equal to 1 plus na. So in WTS, the left-hand side of that inequality has 1 plus a to the n plus 1 power. So what we're going to want to do is multiply both sides of this inequality. Let's multiply both sides of this inequality by another factor of 1 plus a. And let's think about why we'd do that. On the left-hand side, use your power rule. I'm multiplying two powers with the same base. Simply add the exponents. So that becomes 1 plus a to the n plus 1 power, which is the left-hand side of what we're trying to show. And what we're going to do on the right-hand side, we can't avoid it. What we're going to have to do there is we need to FOIL. So if you multiply those two binomials on the right side, product of the first terms gives you 1. Product of the, let's go, inside terms gives me na. Product of the outside terms gives me a. And product of the last terms give me plus na squared. Now let me just keep working here on this right-hand side and say this is equal to. So all I'm doing is working on this right-hand side here. If you look at these two middle terms, na plus a, I can factor out a common factor of a from the right. So this becomes 1 plus the quantity of n plus 1 times a plus na squared. Now take a look. Where we currently are looks a whole lot like the right-hand side of WTS, except we've got this pesky factor of na squared. Now here's what we know about na squared. N, if you recall, is a positive integer. A squared, for any real a, is a positive number. So na squared is a positive number. So, couldn't it be said then that since na squared is positive, that this expression here is greater than or equal to 1 plus n plus 1 times a? this expression here, since plus NA squared is positive, will be greater than or equal to 1 plus N plus 1 times A. So essentially what we just did was we took that positive term and threw it away. We threw it away. And I use that phrase because you're going to see that phrase again in the last theorem. So now look, I've got this is greater than or equal to this, which is greater than or equal to this. So can't we then say that 1 plus A to the N plus 1 power is greater than or equal to 1 plus N plus 1 times A by the transitive property of order. The transitive property of order. Now you might be having issue with me just throwing away that positive term NA squared. And the reason why we can do that is because of this lemma. And it's going to be called appropriately the throwaway lemma. Take a look at what it says. If you've got a positive or 0 y, so y is greater than or equal to 0, then x plus y will always be greater than or equal to x. So if you go back to the previous slide, think of this as your x, think of this as your y. So x plus y will be greater than or equal to x so long as this y is greater than or equal to 0. That's the throwaway lemma. Let's prove this. This is a real quick proof. So let's start with what we are given. Y is greater than or equal to 0. Okay, let's use the addition property of order. Let me add x to both sides. The right-hand side, by additive identity, is just x. Look at that. Got exactly what we're trying to show. Excuse me. We're trying to show this, and we're there. Okay, try your best on those homework problems from 3-1, 5, 9, 21, 29, and 23. Have these ready for Monday. I know there are going to be questions. We'll address those on Monday when I get back. Hope you guys all have a great weekend.